Yeah,
So we're very happy to have Emil Martinec giving us an overview of little string theory.
okay. Little string theory for morons.
Well, I don't know. So I was asked to give to channel David Kudasov and give an overview of little string theory. In fact, there isn't really. So basically, what I'm going to do is present some of the highlights of a line of research that's been going for the last 20 years, and most of it's been done by some collection of Israelis, headed by David Kudasov and Amit Givon. But there isn't really, the only review I could find in literature is something that's actually not on the archive. It's a set of lecture notes from, I think, some lectures given at an IPhT-TV spring school in 2001 called Introduction to Little String Theory. So much of what I'll say is in here. If you go to Inspire and you search for that title or around this time under Kudasov, you'll find a link to a postscript file of the lecture notes. Otherwise, you're out of luck. All right, so what are we talking about? So little string theory arises, it's the theory that arises in the decoupling limit of 5 branes. In string theory. And so, let's see, am I going to want this? Probably. So what are we looking at? So we have some stack of 5 branes. So there will be some directions that are transverse, which are something like R4, and then along the 5 branes, something like R51. And as usual, if we're looking at BPS solutions, they're entirely determined by a set of harmonic functions. There's some harmonic function, I'll call it Z5, and in the string metric, so let's look at NS5 branes, just for simplicity. So minus f of r dt squared plus dy squared plus dx dx. So these are the longitudinal directions, and then in the transverse directions, the harmonic function makes its appearance. dr squared over f of r plus r squared d omega 3 squared. Dilaton is g string squared z5. The 3-form flux that measures the 5-brane charge is the dual in the transverse direction of the dilaton. And basically this is just because, well, the harmonic function is this too low? Okay. 1 plus the number of 5 branes, L string squared over R squared. And F measures non-extremality, 1 minus R0 squared over R squared. Right, and so this is just the volume, so the free-form flux is just the volume form on the transverse angular 3-sphere. And so basically you integrate the flux over the angular 3-sphere, you measure the number of 5 branes N5, and using the usual thermodynamic relations, you measure the energy as the coefficient of dt squared in the asymptotic geometry. So you'll get an energy density, which is an energy density, so energy over the volume of 5-dimensional space. So here is some 5-dimensional space that's along the 5 branes. So if we want the energy density per unit volume along the 5 branes, it's something like 1 over L string to the 6th times the rest energy of the 5 branes. So NS5 branes are solitonic. Their mass goes like 1 over G string squared times the number of 5 branes. And then there's whatever non-extremality you have, R0 squared over G string squared, L string squared. Okay. And then, since this is a black object, it has an entropy. The entropy is just the area of the horizon in Planck units to a factor of 4. So that's what? It's the volume of the 3-sphere. The 3-sphere has radius square root of n5, so we get an n5 to the 3/2. And this is the string metric, so it comes with an L string cubed. The volume of the 5-sphere, the volume of the longitudinal directions. And then e to the 2, the dilaton at the horizon, times L string to the 8th. And so this is going like, so the dilaton at the horizon. So if we're taking a decoupling limit, right, we want this R0 to be small so that this is the dominant term in the dilaton. And so then we can approximate the dilaton by n5 L string squared over R0 squared. And so the n5 will kill 1 power of n5 here, so you'll get n5 to the 1/2 L string times the volume along the 5 branes, R0 squared over G string L string to the 8th, which is just the 10-dimensional Planck scale to the 8th power. And so this is n5 to the 1/2 times L string times the energy density. So the interpretation that was given to this is that underlying the thermodynamics of black 5 branes is something like a string theory of some sort, because it has a Hagedorn density of states. The entropy is proportional. The entropy is proportional to the energy, or the entropy density is proportional to the energy density, either way you want to think about it. But unlike ordinary string theory, so ordinary string theory, if I had an ordinary perturbative string that was highly excited, okay, its entropy would be proportional to its energy, but the scale would be L string. So this is some other kind of string. It's not the fundamental string. It's some new kind of string called the little string, whose tension, so its length scale is square root of n5 bigger than the ordinary string length scale, which means its tension is n5 times smaller than, so there's some kind of, if you like, you can think of this as saying there's some kind of alpha prime little, which is L string little squared, which is n5 times the ordinary n string squared, L string squared. Okay. And so, so the question is, how to think about a theory. So we have, Hagedorn density of states with the string scale square root of n5 times L string, where this is the fundamental string length. And so the question is, how do we think about that?
So, just one question. So, how did you take the decoupling limit here?
Oh, so I haven't said. basically, it's as usual, you want to drop the 1 in the harmonic function.
Exactly. So normally I would just rescale r squared by L string squared, but that doesn't seem to really help.
Yeah, so what you want to do is...
But do you need the decoupling limit? Sorry, all this game is done without the decoupling limit, right?
So far, in this step, right, I plugged in the value of z5 where I dropped this term. Okay. So...
You plug in the value of z5 at the horizon.
Yes.
Okay.
Right. So basically, in order to do that, what did I do? G string squared z5. So the dilettante horizon is G string squared 1 plus n5 L string squared over r squared. I want to evaluate at the horizon, so r naught squared. So to get rid of the 1, I want to take G string to 0. And then to make this non-trivial, I want to scale things so that, so we take G string to 0 with G string squared n5 L string squared over r naught squared fixed. So it's the usual kind of Maldacena limit where you shrink the non-extremality, so you send the horizon scale sort of to 0. And how is this working? Basically, what's happening is the geometry you're sourcing has some asymptotically flat space, then it devolves into some throat, okay? And so there's some asymptotic value of G string, right, where you keep the 1. So if you're far away, r goes to infinity, the dilettante is just G string squared, okay? Then you start going down this throat, okay? As you start going down this throat, the dilettante is growing like 1 over r squared, okay? And so it gets arbitrarily large as you go down the throat. And so the limit we want to take is one where we sit at some scale r naught. We keep that scale fixed, okay? And then we send G string to 0. So what that's going to do relative to this scale, you see the top of the throat going up to r equals infinity. And in the limit, you just have the throat with its growing dilettante. And so this scale just gets pushed up to r equals infinity.
I see. So this is different from the usual decoupling limit where you're sending the string length to 0.
Yes.
So here I'm keeping the string length fixed. Is that what you're doing? Or you're keeping r naught squared in? Yeah. So
Hold that question. The answer is the answer is yes. We're keeping. So there's some. I think the way I'd like to say it is that let's define some r hat, which is r naught over G string. That's the scale that we're keeping fixed, right? And so in addition, we're saying that n5 L string squared is fixed. Okay, so what do I mean by that? What I mean is, as usual, this is dimensional, this is dimensional. If I want to say something is fixed, I should be talking about a number. I'm going to keep the ratio of these two scales fixed, okay? Which means that I'm keeping the little strings in the game because their tension is finite in terms of the energy scales I'm talking about. And I'm keeping, of course, the non-extremality around to talk about. Okay, but indeed it is something where you haven't decoupled all stringy things in the geometry like you would in, say, n equals 4 Yang Mill. To take the limit that takes you to ADS5 cross S5, you're sending the horizon scale to 0 relative to the asymptotic L string. Here we're not doing that, right? We're not keeping energy scales small relative to L string. We're keeping that scale in the game. And so that's why the limit is not going to be a field theory, it's going to be a string theory. Okay. A cartoon that I like that explains, at least in heuristic terms, where this scale is coming from is to take the M-theory limit. So suppose we were doing this in type 2A. We could take, it's kind of schizophrenic, right? I'm saying let's take G string to 0, so that doesn't sound like an M-theory limit. But ultimately, somewhere way down this throat, right, if R naught goes, there's some scale of the dilaton at the horizon, right? So there's some e to the 2 phi at the horizon, which is what? It's n5 L string squared over this R hat squared. Eventually, that's going to get big, right? And so if I make the non-extremality small enough, then eventually I get to some strong coupling limit, and the physics near the horizon is going to be governed by M theory and not type 2A string theory. All right, so then I should be thinking about M5 grains. And there's an extra circle in the game now, which is some direction parameterized by some 11th dimension of size R11. And in that circle, the 5 branes in M, so the NS 5 branes lift to M 5 branes in M theory. Okay, so they're point-like in the extra dimension. So they live they live at particular places. Okay. And then what's the fundamental string? The fundamental string whose tension I've kept around is an M2 brane that wraps the 11th dimension. So here's M2 and M5. And so we can, these can undergo a transition where these are a stack of M5 branes. Right? The M2 brane can end on M5 brane, and so it can do something like this. Right? So if I add now the longitudinal directions along the M5, right? What's the picture? Let's do it over here. No, let's do it up here. So our M2 branes are little strips. And each strip you can think of as, it's got one long direction, which is, because after all, this direction is 11-dimensional Planck scale size. And this direction, is some long direction along the 5 brane. And so this is effectively a string. So it's sort of energetically cheap wiggles are to wiggle the 5 brane this way, rather than to try to wiggle it this way. That costs Planck scale energy. So it's effectively a string. But what is its tension? Well, we've chopped up the fundamental string, which is an M2 brane wrapping all the way around. Okay, so its tension, so L string squared, is the tension of the string is 1 over L string squared. And that's R over L Planck 11 cubed. Okay. And we've just chopped that into N5 bits if these 5 branes are roughly equally spaced around the 11th dimension. Okay. So that's kind of a heuristic explanation of where this tension fractionation is occurring. Right. So this is mu string little will be R over N5 L Planck 11 cubed. And that's a qualitative explanation where this is coming from. Now, for what we're going to do a little later, we can take this picture back down to, so M to type 2A in two different ways. One is we can just re-reduce along R11. Okay, that gives us the picture. So this is along an S1 that's perpendicular to the fibranes. Okay, that gets us back down to type 2A with, again, our starting point, fundamental strings and NS fibranes. If we, however, decided to dimensionally reduce back down to 2A along some circle that was along the fibranes, right, then an M5 brane compactified on a longitudinal circle becomes a four-dimensional object. So that will be a D4 brane. And the F1, which was a membrane in 11 dimensions, well, we've compactified in a direction that's perpendicular to the membranes, so they stay membranes, so those are D2 branes. So depending on what duality frame you want to look at things, the same sort of configuration of brane bound states can be either realized as F1 NS5 or D2 D4. Okay, and then these become with D2 brane strips. Okay. As the structure of the bound state. And of course, we can take this picture and further T-dualize it in say this direction along the fibranes. So this, under a T-duality along the D2, will become the D1, D5 system. Okay. And so by various duality chasing arguments, you can get back to the D1, D5 dynamics that's of interest for thinking about, for instance, ADS3 times S3 that many people here know and love. Okay. So there are sort of many pictures of what these little strings are. Here, there's some kind of fractionated membranes in M theory. Here, after all these dualities, the dynamics on D5 branes is 5+1 dimensional super Yang-Mills theory. And the D1 then becomes some kind of solitonic string inside the D5 brane. Well, what's a natural soliton if you're thinking about Yang-Mills theory? So 5+1 super Yang-Mills has instanton solutions. Instanton is something which is point-like in four-dimensional Euclidean gauge theory. Okay, so if I just say I have some kind of R4 along the fibrane, and then there's some direction here, so I can think of the Yang-Mills instanton as being some kind of object that's localized in four of the five directions along the fibrane. Okay, and one of the moduli of the instanton is where it is in those four directions. So I can let that adiabatically evolve along the other direction, and that will become an effective string. Now that's a description of actually the full D1 dissolved in the fibrane. And then what is a little less clear, but is nevertheless true, that an instanton in UN gauge theory in 5+1 dimensions can fractionate in the same way that we've seen here, sort of geometrically in the M theory picture. And so the description of, we have some kind of UN 5 super Yang-Mills theory, is that supports some kind of fractionated instantons. You can break the instanton apart into N5 pieces, and each one of them can evolve independently.
I have a question. So when you T-dualize from D2 D4 to D1 D5, you're basically having the picture above, the green one with the strips, and you're basically dualizing in the transverse direction, in the perpendicular direction, right? To make the
I'm
to grow the
dualizing
D4s.
in
So
this
that's
direction.
to begin with, to go to D to D4.
Yes.
And then in D to D4, the
D
picture
to
is the
D4,
same.
the picture is just like this. These are
And then
now
if
the
you
D4s.
dualize in the transverse direction to get to D on D5. You want to grow the D4s and to shrink the D2s.
You're right. Sorry. Yes.
And then when you do that,
Yes.
but then normally when you do that, I mean, you know, if you look at the generic configuration of little strings, you know, when you have one D2 strip here and one D2 strip there, on the D4 word volume, there will be various fields which are going to go from one of the tiny strips to the other tiny strip, because, you know, you have a D2 ending, and, you know, they can move around, you know, they are free to move, but on the D2 word volume, on the D4 word volume, there will be various, and when you T-dualize those, you're basically saying, so that's like a 2-form field strength. I'm just wondering, so there's a 2-form field strength on the D4 word volume, and then when you T-dualize it to the D on D5, it becomes non-abelian, or, I mean, I'm just confused.
Yes, it becomes non-abelian. So this thing, so that's where, one way of thinking about the fractionation is there's some particular SU2 inside the UN, and inside that is where the gauge fields on this brane and on this brane are getting turned on because this guy is a source for those gauge fields. Okay, so you're in a limit here where that structure has been Higgsed by separating the 4 branes apart.
I see, okay.
So when you push the 4 branes together, that object becomes light, and just becomes some non-abelian SU2 instanton inside the UN. And so that's how you can think about the fractionation, is that, you know, roughly speaking, an SU2 inside the UN5 is a 1 over N5 effect in the full matrix of the gauge theory. And you have to combine N5 of those SU2 bits in order to make something that has no charge under the UN and only charge under the U1. Sorry, no charge under the SUN5 and only charge under the U1. And that's how you combine things back together to make something that's unfractionated. Okay. Right. So what are we doing in taking the decoupling limit? There's some, in this picture of 5+1 gauge theory, right, there's some Yang-Mills coupling. Well, in general, if I have a DP brane, and I ask what's the Yang-Mills coupling that I get out of the low energy limit of the D brane dynamics, it's G string, L string to the P minus 3. In other words, Yang-Mills squared is just G string if I'm on a 3 brane, and otherwise it gains dimensions which are normalized by L string. So this becomes G string, L string squared in 5+1 D. Okay. So this is the inverse tension of a D1. Okay. Right. So that is consistent, right? Here what I did was to say, okay, I take the decoupling limit of NS5 branes. I want to keep this scale. So what did I do here? I took G string to 0 with the scale N5 L string squared and R hat squared fixed. Okay. So the natural object here was the fundamental string with its tension scale L string, and so here, after this whole sequence of dualities, the F1s turned into D1s, the NS5s turned into D5s. And so I've done I've chased through a whole bunch of dualities and ended up at the end of the day just doing S duality. Okay? So if the limit here was to hold the fundamental string tension fixed, the limit here is to hold the D string tension fixed. Okay? Which makes sense. It's the coupling of the Yang-Mills gauge theory. If I want non-trivial dynamics in the infrared, I better be holding the Yang-Mills coupling fixed, okay, as a relevant energy scale. Okay? So here, the decoupling limit is G string goes to 0 with G string squared, L string squared fixed. And that's S dual to G string goes to 0 with L string squared fixed.
There's no square on the string,
right? Or just more generally, there's some effective string tension. The relevant string has some tension scale. Whatever that relevant string is, basically we're taking a limit. So it's always G string goes to 0 with some kind of effective string length times the energy scale fixed. Okay. Now, because we're keeping a string in the game,
You can write on the board on the left, I guess. You can write on the board. I don't know, Mariano.
No,
I think we're done with
You
this.
can write whatever you.
But because we're keeping a string in the game, what we're left with as our decoupled theory is not a quantum field theory, it's a string theory. Right? So because the decoupling limit keeps somebody's string tension fixed, it is not a local quantum field theory. So it's a somewhat more sophisticated version of gauge gravity duality than we're used to. In particular, if we compactify the longitudinal directions, the decoupled theory exhibits T-duality. Okay, and that by itself is telling you what you're getting in the end of the day is not a local quantum field theory. That there's some scale, there's some fundamental scale of order L string effective. If you tried to scatter things at energies above that scale, they would be fundamentally non-local on that scale. Okay. But it's also not a theory with gravity. It's dual to a theory with gravity in the usual Malvasena sense. And the way to think about that is that, so if this is basically because G string asymptotic went to 0. So it's kind of a weird situation where the asymptotic G string is 0, so you've indeed decoupled bulk gravity in that sense. There's no fluctuating graviton asymptotically. But, you know, at finite depth down the throat, there is a finite G string, right? We just you know, the string coupling, so what, right, the dilaton is basically n5 in my original duality frame, n5 L string squared over the scale that I've kept fixed squared. Okay, so it's finite at finite r hat, and so in some sense there is bulk gravity running around. Okay, but the idea of if our usual story about how decoupling limits work, it's that you've decoupled the asymptotic gravity, and the gravity that exists in the throat is itself some kind of collective phenomenon of the decoupled non-gravitational theory. Right? In the same way that in the decoupled ADS 5 cross S5, there is bulk gravity, but it's dual to the dynamics of the gauge theory, and if you solve the strong coupling dynamics of the gauge theory, gravity would pop out as a collective effect. And so that's the sense in which there's gravity down the throat. It's some kind of collective effect of little string theory. Okay. Let's think a little bit about the Penrose diagram of our decoupled theory. So what was our metric after we took decoupling? It's minus dt squared plus d rho squared, where rho is square root of n5 log r. Plus our longitudinal directions, dy squared plus dx dot dx, which may or may not be compactified. Plus n5 L string squared d omega 3 squared. And the dilaton is rho over square root of n5. Okay. So if I'm interested in the dynamics of things running up and down the throat, the radial direction is a free field with a linear dilaton. Okay, and so the dynamics in the RT plane is just a two-dimensional Minkowski space, right? So we're used to taking decoupling limits and having some kind of time-like boundary that is where the dual gauge theory lives. And I hate that terminology. Anyways, the UV of the gauge theory is dual to dynamics near the asymptotics. Okay, and so that's time-like, right? So I have local quantum field theory, and so to get things to localize in the gauge theory, I'm going to the UV, and that's things that are near the boundary. Okay, and so since the gauge theory has some time-like dynamics, the local physics in the UV should be time-like. Here it's different. There's some. It's basically two-dimensional Minkowski space, and as I take rho goes to infinity, I reach the boundary, and it has to look like this. And then there's some region, rho. Sorry. Yeah. Okay. And so there's some region rho goes to minus infinity where e to the 2 phi, e to the minus 2 phi blows up, and so this is some kind of strong coupling region. Okay, so there's some kind of strong coupling. That's in here that we aren't going to be able to understand in using perturbative string theory, but it's there. Okay. So in this sense, this fancier version of gauge gravity duality is in some sense closer to what you would dream of in terms of flat space holography. Right? Because at least topologically, the Penrose diagram is the same as you would have for flat space. But it's, so it's sort of closer to flat space holography. You could ask, is it closer to the flat space-time limit? It's not quite that yet. So it's so yes and no. So yes, there is non-trivial scattering. So in usual ADS-CFT, if you have something, some massless excitation in the bulk, it travels out to the boundary and comes back into the middle in finite time, as seen by a boundary observer. Okay. Here, you can have scattering, whoosh, and it takes an infinite amount of time for something to propagate into the middle and go back out, because it's, after all, it's just Minkowski space.
Didn't I say I said 2D Minkowski as opposed to 6D Minkowski?
I'm focusing on this part. Just the dynamics in the RT, the radial and time directions.
But in principle, because for Minkowski
So of course, as usual with any Penrose diagram, right, there's a whole host of other dimensions you're suppressing in order to draw it on a blackboard.
Yeah, I'm asking in the sense that there are, in this sort of not quite proposals of flat space holography, people were taking very seriously the sphere, living at infinity, and looking at some sort of conformal structure, case in which the difference between 2D and 6D would be important, I guess.
You can put a K3 there, for example, instead of a T4 if you want. And then it's really 2D. Or you can put a T4 or you can decompactify it.
I mean, this is just a random comment saying that.
Yeah. So I mean, it's different in the sense that the size of angular spheres is not growing. Okay. So in that case, so the no is that the volume of space is not diverging towards the boundary. Okay, and so that actually has quite a few effects. And in addition, of course, there's this strong coupling region. So, right, if you just send wave packets in to this decoupled geometry, they run in to hit some strong coupling region unless they have a rocket ship that sends them back out. And then you have to say, okay, how do I deal with what's going on here? Okay. So if you write down the usual string theory effective action in this geometry, and again with the three-form flux is still star in the perpendicular direction phi. Well, it's then obviously constant. It's just basically the volume form on the constant size 3-sphere. So if you say, okay, what's the wave equation that governs the dynamics of low energy degrees of freedom in this geometry, you find that the dimension of anything like e to the perturbation that goes like e to the alpha rho is going like alpha q minus alpha, where q is this slope of the linear dilaton. Okay? So any of you who've done worldsheet string theory calculations, usually the dimension of an exponential is just, so usually without linear dilaton, right, the dimension of an operator like e to the alpha rho is, minus alpha squared up to some normalization. So if I have, if I have a plane wave e to the I alpha rho, okay, that's just the usual spectrum of the Laplace operator, right? But with the linear dilaton, things get shifted a little bit. There's a linear term in the stress tensor on the world sheet, and so you get this shift. And so that means that that the scattering states are asymptotically is some psi that goes like e to the minus q over 2 plus I lambda times rho. Okay. Well, plus or minus. Okay. So, radially incoming and outgoing plane waves get shifted from zero momentum by some imaginary amount, and when you work through what's the energy cost, what you find is that this is a continuum above a gap, and the gap in the energy squared is of order n5. In fact, more precisely, m gap squared is like n5 over 4 Bellstring squared.
So those are the dimensions. So so if you just write down string theory in this background, you're saying that this is the. So this is a result which is.
Yeah. So
in the bulk, but it's a bulk.
It's a bulk computation, and so I should say this theory with linear dilaton, constant radius, 3-sphere string theory in this background, perturbative string theory in this background, naively, is exactly solvable, right? This is a free field. This is a free field. The linear dilaton doesn't affect anything. It's just some improvement term in the world sheet stress tensor. This is flat. This is flat. This is a 3-sphere, but it's a 3-sphere with a very particular 3-form flux through it, which means that the world sheet theory has a B field. Well, the 3-sphere is just the SU2 group manifold, and this is the torsion that parallelizes that group manifold. So this part of the theory is just the SU2 Wesson-Witten model, and the rest of it's free field theory. Okay, so this was an observation of Cowan, Harvey, and Strominger in the late 80s, early 90s, that string theory on this background is, let me put it in quotes, exactly solvable. Right. Different people have different standards of what exactly solvable is. Here, exactly solvable means you can compute the perturbative spectrum. Okay, so now, of course, that's silly, right? There's a region of strong coupling where perturbation theory is breaking down, and any wave packet you send in, any plane wave you send in, hits the strong coupling region, and perturbation theory dies. So there is no perturbative S matrix that makes any sense whatsoever. Okay.
I didn't understand your calculation of the gap. So isn't it just like something like q squared?
Yeah. And
if q, I'm a bit confused that q seems to be 1 over square root of n5, or?
q is 1 over square root of n5.
Gap goes to 0 when q goes to 0, right?
Gap goes to 0 when, yeah, what am I doing wrong?
I guess the question is, how does the gap go with the number of n5?
Yeah, it should go the other way.
It should go the other way.
And that follows, so then maybe your equation Q goes like 1 over n5 is correct, and it's just that the formula for m squared gap is wrong.
No, the formula for m squared gap is right. I think where I screwed up, this is definitely the right formula for the dilaton. What I may be missing is an n5 here.
Probably yes, because rho is mentioned.
There's definitely, well, I put, no, this is right. This, rho over n5. So what was my dilaton? My dilaton was e to the 2.5 is n5, let's ignore the, let's just set L string to 1 over r hat squared. So this is n5 e to the 2 rho over n5. Okay, so up to some factor of 2, this is certainly correct. This is certainly correct. Yeah.
But maybe I just wanted to check, so okay, so m squared gap, is it just like q squared, and then somewhere in the formula there should be something, so you're sure that the end result that you wrote there for m squared gap
This is definitely correct.
Okay, then I mean we can
And so I just made some mistakes. I think it may be, I maybe screwed myself up in rescaling rho. So that doesn't sound quite right either. Q is root n5. Oh, right. Yeah, I screwed up somewhere, but this is definitely the right result. Let me.
There should be some n5 in rho, otherwise rho over a square root of n over m5 doesn't have any n5. So rho is probably n5 log of r hat.
Yeah, that's that's right. That just comes from here, right? Phi is rho over n5. And I do want to define this. And the metric came from some z5 dr squared, which is like n5 dr over r squared, which is like n5 dr hat over r hat. Right, which is like d rho squared. So anyway, let me not get too hung up on that. I guarantee you this is the right result. I'll come at this from another direction later, which will make it obvious. because it turns out that the spectrum here is closely related to the continuous series spectrum of SL2R. So you might recognize this from, if those of you who know SL2 representation theory, where dimensions of plane wave representations of SL2R are half plus I times something. So this is coming from the same sort of place. And so yeah, so let me come back to this after developing some more stuff. And so I would like to, change gears a little bit. And ask if there's another way of getting 5 plus 1 dimensional super Yang-Mills theory. And that is to consider an ALE singularity in 4 Euclidean dimensions. Okay, so for instance, an AN minus 1 singularity has n minus 1 vanishing, and by vanishing I mean in string theory stringy, 2 cycles. Call them sigma A, with A equals 1 up to n minus 1. And now we can think about, so this is some nice, supersymmetric background of string theory, and one of its nice features is that it has anti-self-dual forms. Call them theta A, which are, let me call them theta A, A minus 1, which are, well, you'll see the reason for the notation in a minute. That are localized on or near the vanishing cycles. Okay. And so you can make a Coates-Klein ansatz, in quotes. I mean, this is a non-compact space, but it has some kind of localized structure. And then you can ask, is there something interesting associated to that localized structure? And the answer is yes. So if we consider type 2A on this singularity, then we can construct gauge fields, A mu, A minus 1, which are the usual 3-form potential, Ramon potential that lives in type 2A string theory, where we contract 2 of the indices against the holomorphic 2-form. So this is something that depends on the ALE coordinates. Okay, and it's localized near the structure at the bottom of the ALE space. And then we can let this C mu nu lambda vary over the R51 that is the directions that are there's some directions that are transverse to this singularity. Okay, and we can let this structure wiggle adiabatically as we evolve in those directions. Okay, so this is a Kaluza. If this was a compactification, this would be a Kaluza-Klein ansatz for a gauge field in the lower dimension. Okay, but even if it's a non-compact thing, because this thing is localized appropriately near the singularity, you can say I have what's effectively a phi plus 1 massless gauge field that's bound to the singularity structure. Okay.
So if you have the 6 branes in 11 dimensions, they give me the singularity in 11 dimensions, and then that's basically the M theory.
For instance.
So this would be, so if I uplift the 6 branes, I get these bubbles, and then this is the M theory 3 form contracting with those. What does it become? And this, and then in type 2, this becomes the gauge field on the D6 branes, right?
Yeah, it would be the gauge field on. Well, so gauge fields on a D6. Yeah. So right. You're doing some kind of 9/11 flip where you take a D6 brane, you lift it to M theory, and then you compactify
yes.
back down on a different circle.
On a different direction, yes.
Yeah.
But if I just play this AD game in 11 dimensions, which I can do, by doing this, if I do this, I just get the uplift of the D6 brane word volume gauge fields.
Mm-hmm. So that's another way of seeing that there's going to be such a gauge theory, indeed. Right. Okay, so that's one thing. So we get basically a collection of U1 gauge fields, as many of them as the rank of the singularity. So if you like, the rank of, I have a U1 to the n minus 1. Now, in addition, well, I have topology. So I can wrap branes around that topology. So we also have D2s that we can that wrap the sigma A's. Okay. So the reason I call this theta A minus 1 is that you should think of this as that there's some collection of there's the resolution of this singularity sort of inserts this many two spheres into the geometry and blows things up a little bit. Okay, and so if I wrap a D2 around one sphere, it's charged under two of these gauge fields. Okay. It's sort of charged under the one labeled by A and the one labeled by A plus 1.
So in Gibbons, sorry. So the theta A's are they go on a 2 cycle, so they are the fluxes which go on a 2 cycle. And the sigma A's are what?
Sigma A's are the topological cycles. It's a basis for the cohomology of the singularity.
And they're just, if you put the points in a line, the sigma A's are just the 1, 2, 2, 3, 3, 4, 5,
yeah.
and so on. And the thetas are
the anti-self-dual 2 forms in the geometry.
But why do they care about A and A minus 1? So A is labeling you're not labeling the Gibbons working centers, right? You're not labeling there are n Gibbons working centers. There are n minus 1 cycles between them. Theta is wrapping one particular 2 cycle.
Yeah, what do I want?
So say there's an A, but then indeed the 2 cycle has an intersection with the other nearby 2 cycles. So an object, so D2 brane wrapping, I think that's, so D2 brane wrapping, let's say the 2-3 cycle, is going to talk to the theta, is going to be charged under the theta wrapping the 1-2 cycle.
Right. So you claim these guys should also be labeled by pairs of A's.
Just A, yeah. But then it's the nearby ones.
Yeah, yeah.
It's the nearby ones.
Right. So the point being that that these D2s are basically bifundamentals of this U1 to the n-1 gauge theory. Okay. But I'm in type 2A. These D2s also live in vector multiplets of the effective. Right? So again, what are these D2s? I have a whole collection of directions, R51, that are along this singularity. So if I wrap a D2 around the singularity, it's still free to move in 5+1 dimensions. So these are some kind of particles that are charged under this 5+1 dimensional U1 to the n gauge theory. Okay, and so what are they? They're basically the quanta. Oh yes, and I should say that if you ask yourself, kind of what's the what sort of supermultiplet does this 5+1 dimensional particle-like object live in? It lives in a vector multiplet, if you trace it through. And so basically these are some kind of 5+1 dimensional vector quanta. Okay. And clearly, as I go towards the singular limit, where I blow down all the 2 cycles, all of those particles become massless. So what are they? They're vector supermultiplet quanta that are charged under U1 cross U1. They're just the W bosons of some enhanced symmetry. And when I'm looking at the limit where the 2 cycles are blown up a little bit, I'm looking at the Coulomb branch of that 5+1 dimensional gauge theory, where the blowing up has made the W particles massive. And the masses are just proportional to the sizes of the 2 cycles. Okay. So D2s wrapping the sigma A are, they live in 5+1D vector supermultiplet. They're, if you like, they're quanta of the 5+1 dimensional vector supermultiplet. And their mass is the volume of the 2 cycle they're wrapping divided by, well, it's a D brane, so it's G string, L string cubed. Okay? That's the mass of some W boson that's associated to the 8th cycle. And so we can take, so basically what we have, if we made a quantum field whose quanta are D branes, then this would be 5+1 super Yang Mills on the Coulomb branch. So now we can take a decoupling limit. Right, so right now this is just some ALE singularity. I haven't decoupled gravity. The asymptotic, this is some conical space-time geometry, and clearly, string theory in the ambient, ALE space isn't decoupled. So in order to do that, I need to take the decoupling limit. What's the appropriate decoupling limit? G string goes to 0 with M W A fixed in terms of whatever energy scale I want to keep around. So this should ring a few bells from earlier in the lecture, right? What do? I want to decouple the ambient string theory, so I just turn off the string coupling so the strings don't the strings that are living out here stop interacting with each other. The only non-trivial dynamics is the dynamics near this singularity, okay, where I've focused in on things that are bound to that singularity and kept their energy scale around in the dynamics as I take the limit. So there's non-trivial interacting dynamics in the vicinity of the singularity, but everything else has been decoupled. Okay. So then we could ask, okay, is this the same or different than the decoupling we talked about earlier? Right? We've got 5 + 1 super Yang-Mills, two different ways of getting at it. Are these two different theories, or do I have, two versions of holography that involve 5 + 1 super Yang-Mills, or is there just one? And the answer, of course, is there is only one. And so this is two different ways of thinking about that same decoupled dynamics. One is in terms of decoupling dynamics near some kind of Calabi-Yau singularity, and the other is dynamics of fibranes. And so this leads you to suspect. So this is this. So this is an alternate.
But before we didn't have super
Or if you want dual presentation of little string theory. Secretly.
Before we didn't have 5 + 1 super Yang-Mills, before it had an NS5 brane.
I had an NS5 brane, but in NS5 brane, when I take the decoupling limit, the low energy dynamics on a stack of NS5 branes in type 2B is
In 2B.
is 5 + 1 super Yang-Mills.
Oh, in type 2B, not in type, okay.
Right. So, which leads you to say, what is the duality that relates these? Here it's type 2A on some Calabi-Yau singularity. The earlier presentation, the way I got super Yang-Mills was to think about type 2B on NS5 branes. So they should somehow be T-dual to one another in some incorporated sense. So T-dual, in some sense, presentation of little string theory. How are we doing? Right. So, yeah. Right. So what I'd like to do for the rest of the time is to explain how we understand this duality using worldsheet string theory. And then that will sort of introduce some of the worldsheet techniques that one uses to do calculations that tell you something. Okay.
So I
Yes.
just don't ask a really dumb question. So at the beginning of the talk, so you went from this NS5 F1 system to M3 back to D1 D5, and this is where I thought that the 5 + 1 square Yang-Mills was coming in.
Mm-hmm.
And then you're doing an additional S duality on that in order to get this T-dual presentation?
So,
and I guess the question is, if that's what you're doing, does this commute to the decoupling limit?
so what are the different systems that we have? So we have NS5 in 2B in decoupling limit. So that is going to give us 5 + 1 D super Yang-Mills. And then we also have type 2B type 2A, excuse me, on an ALE singularity in a very similar decoupling limit, okay, that also gives 5 plus 1D super Yang mills. And so what's underlying this, I think at the end of the day, is that if you have NS5 grains, if you have a circle, and you have a bunch of NS5 grains that are transverse to that circle, and you do T-duality, they become a stack of KK monopoles on the T-dual circle. And at the core of a bunch of coincident KK monopoles, there's an AN singularity. So roughly speaking, that's kind of the heuristic explanation for why this is working. Though the details, as we'll see, differ in some respects.
Monica's question, I guess, was about the little string theory. So little string theory comes from NS fibrils in type 2A.
Ah, right.
So where do you put that? I mean,
right. So,
Yeah, how did you get to the statements? My confusion is how do you...
it's at some point in my chasing through various dualities.
You ended up with D1, D5 at some point.
At some point, I ended. So right. So if I S-dualize this, I would have
D5.
I would have I would have 5 plus 1 gauge theory on a bunch of D5 grains, and the thing I'm holding fixed in the limit is the tension of the D string.
So you're saying that if you trace through that set of dualities and do a final S duality, to get to an S5 and 5, and you're very careful about the decoupling limits and blah blah, you're going to end up precisely on the correct decoupling limit after
Yes.
that change of duality.
Yes.
You can also do a T-duality on NS fibril in type 2A, which
Exactly.
is
So
probably
you're
much
willing to
easier.
compactify one direction along the type 2A NS5 grain. T-duality in a longitudinal direction to an NS5 does nothing. It just changes 2A to 2B. Okay. What will change, of course, is that 5 plus 1 super Yang mills is a theory with some scale. In this case, the scale is L string squared. Is sort of the dimensionful scale of the Yang mills coupling here. And if you go to energy, if your 5 grains are non-compact, and you go to energy scales much below this scale, the Yang mills coupling is irrelevant in 5 plus 1 dimensions, and so the theory just becomes free in the infrared. If, on the other hand, you're in the type 2A version of this, now the low energy theory below this scale is the 2-0 tensor theory. And so there's a non-trivial infrared dynamics, which is the 2-0 super conformal theory in 6 dimensions. So depending on what duality frame you're in, when you ask, what in the space transverse to this, right, there's some throat with a growing dilaton, and we decoupled the asymptotic region to get the full linear dilaton throat. Down at the bottom of this linear dilaton throat, there's some strong coupling dynamics. What is it? Well, in this duality presentation, it's just some kind of trivial theory, though it's a little hard to understand how. And in the T-dual dynamics, you take a different infrared limit than what's sitting down at the bottom here is the 2-0 tensor dynamics. But that's all below some scale, which is set by where you are in the throat. Okay. So I'd like to continue sort of assembling bits and pieces of information, and hope you'll bear with me. I promise they'll all be tied together in the end. So there's something called the Calabi-Landau-Ginzburg correspondence, which is work that I and Nick did independently in the late 80s, that was very nicely explained in a groundbreaking paper at Witten in '92. So we're interested in thinking about Calabi-Yau singularities. What do they look like from the point of view of string theory on the world sheet? So an example of an Lie singularity, well, I'll get to Lie singularities in a minute. Let me think about Calabi-Yau n-fold, which is the hypersurface z1 to the n plus z2 to the n plus dot 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 plus zn to the n equals 0 in CP n minus 1. And so think of these as the homogeneous coordinates on complex compact projective space. And this is some polynomial I'll call P of Z. Okay. And so one of the earliest examples, in fact, one of the few examples that was known of higher dimensional Calabi-Yau spaces was if you sit in CPN and you restrict yourself to the hypersurface that solves this equation, that is topologically a Calabi-Yau manifold. The metric is not the metric on the hypersurface that you would induce by pulling back the metric on the ambient projective space is not the Calabi-Yau metric. The Calabi-Yau metric is not known, but one can prove that it's topologically in the same category. Okay, and so we can describe this in worldsheet string theory by writing down a U1 gauged linear sigma model, which is a fancy way of saying that treat these as complex fields in some n equals 2 hypermultiplets living on the worldsheet. And so we're going to write down a sigma model with z's having zi having charge 1 under some U1 gauge field, and an additional Lagrange multiplier field which will have charge minus n. And so we can write down a superpotential, which is lambda p of z, that has charge 0. So it's a gauge invariant thing you can add to the Lagrangian. And so this theory has when you write down the gauge kinetic term, there's a d term constraint, which is that 0 is equal to the sum of the absolute zi squared minus n times lambda squared minus zeta, where lambda is the lowest component of this Lagrange multiplier field, and zeta is a phi Eliopoulos term for the U1, the coefficient of the Fi term. So what does this do? Well, if you're going to solve the D-term constraint, there are two regimes. So limits. There's a limit where zeta is large and positive. So in this regime, if you try to solve the constraint D equals 0, well, zeta is large and positive, so you have a big negative number here. This just makes it more negative. So the z's had better be one of the z's better be non-zero in order to solve the D-term constraint. So some Zi is not equal to 0. But then if you look at the bosonic potential you get from this superpotential, right, what is it going to look like? It's basically the absolute value of p squared plus the absolute value of lambda squared times dp dzi squared summed over r. So one of the z's better be not 0. So this is not 0. So in order to minimize the potential, lambda has to be 0. To minimize v. Okay, but then if lambda is 0, what does the deterrent constraint say? It says that the sum of the z-squareds equals zeta. Okay. So this condition modulo the U1 gauge transformation, which sends z to e to the I alpha z, this is a standard presentation of CPN minus 1. Right? It's the, roughly speaking, this space absolute z squared equals zeta is a sphere in R2n. And then quotienting by the U1 action kills phase direction. So if you write the Sn minus 1 as a circle fiber over Cpn minus 1, this just gets rid of the circle. Okay? So at the end of the day, the minimum of the potential modulo gauge transformations is Cpn. And the Lagrange multiplier, lambda, sets p equal to 0 in Cpn. And Cpn minus 1. So this is exactly a way of describing this Calabi-Yau manifold as the low energy dynamics of this sigma model. So the Calabi-Yau is the low energy nonlinear sigma model effective theory. Now, it's not spot on, because once again, what you would deduce from here is that the metric of that sigma model is the metric that's induced from the ambient Calabi-Yau projective space geometry. Right? This gives you metrically the projective space, and this p equals 0 carves out that hypersurface in that space, and so pulled back the metric on the low energy field space would be the CPN metric pulled back to p equals 0, which is not the Calabi-Yau metric. So when I say the low energy dynamics is the Calabi-Yau, what I mean is that you're in the universality class of that conformal sigma model. And as you flow the theory to the infrared on the world sheet, that flows to an infrared fixed point, and the infrared fixed point is string theory on that Calabi-Yau manifold. Okay. Anyway, so that at least will, but things that are robust topological properties, like the existence of various vanishing cycles and so on, will already be apparent at the level of the UV gauge theory. Okay. So that's one limit. Another limit you could take is zeta much less than 0. What's the low energy dynamics then? Well, now zeta is large and negative. The only negative term here is this one. And so in order to solve the deterrent constraint, lambda better not be 0. But now, if lambda is not 0, this term is active in the potential, And the only way you can solve it is if you set the z's to 0. Okay. Okay. Then you come back to the deterrent constraint. The z's are 0. Zeta is huge and negative. So lambda is approximately...
Ici, Michel Dédouchel, directeur du centre. Chers collègues, la participation aux élections professionnelles est passée à 44% au CEA Paris-Saclay à 11h. Nous approchons du quorum et peut être atteint. Il ne manque plus que 207 votes en annexe 2 et 268 en annexe 1. Il est encore temps de voter jusqu'à 14h ce jour. Si vous avez oublié vos codes, il est très facile de les obtenir soit à partir de l'intranet du centre, soit en appelant 02 96 50 50 00, soit en vous connectant sur le site CEA webvote.fr. Je compte sur votre mobilisation pour atteindre ce but.
Apparently they're going to give us some prime d'intéressement, which is going to be lower if the... So everybody votes and they're blackmailing us. They have to double, they have to repeat, of course.
Ici, Michel Dédouchel, directeur du centre. Chers collègues, la participation aux élections professionnelles est passée à 44% au CEA Paris-Saclay à 11h. Nous approchons du quorum, il peut être atteint. Il ne manque plus que 207 votes en annexe 2 et 268 en annexe 1. Il est encore temps de voter jusqu'à 14h ce jour. Si vous avez oublié vos codes, il est très facile de les obtenir soit à partir de l'intranet du centre, soit en appelant le 02 96 50 50 00, soit en vous connectant sur le site CEA webvote.fr. Je compte sur votre mobilisation pour atteindre ce but.
Okay. Right. So, in the end of the day, after you solve the deterrent constraint and plug it back into the potential, so lambda gets a VEV, okay, and so now the superpotential and low energies is just this. So the dynamics here is dynamics of a bunch of fields with a trivial kinetic term in some superpotential, which is P of Z. Okay. So two different regimes. And you say, well, why should I care? Zeta is just some parameter. It's the Fi term in some gauge theory. And I've already said that gauge theory is not conformally invariant. So in principle, this Fi parameter is not something that's fixed. It's something that runs with energy. And so, well, it either runs to here or it runs to there. But it just so happens, and this is one of Witten's great insights, is that if the manifold that's carved out by the equation P equals 0 in CPN is a Calabi-Yau manifold, then this zeta parameter is marginal. It's a modulus. So the infrared dynamics can either be here or here. It's your choice. They're both somewhere in the moduli space of Calabi-Yaus. And what is this zeta when you trace it through? Zeta is the size of some particular two-cycle in the Calabi-Yau cohomology. It's a Kähler modulus. Okay. So what we're describing is two limits in the Kähler moduli space of the Calabi-Yau. One where that two-cycle is big and floppy, where the thing looks like a nonlinear sigma model. And another where you blow down that two-cycle to substringy scales. And the thing looks like an ordinary scalar field theory on the world sheet with a superpotential. So this is something that it sounds striking, but we know in string theory, when things get stringy, your geometric intuitions start to fail you. And what's the thing that's failing you is that here it's a nonlinear sigma model. So the only couplings in the Lagrangian are, G mu nu, dx mu, dx nu. plus an asymmetric coupling, right, to the B field. Right? So that's your S world sheet. Right? It's just derivative couplings to some geometric fields that live in supergravity. Here, when I say I've got a superpotential on the world sheet, it's like I've written down a tachyon on the world sheet Lagrangian. And ordinarily you say, oh, this string theory doesn't have any tachyons. Well, actually, string theory can't have tachyons if they survive the GSO projection on the world sheet. And so this is an example where the GSO projection allows this particular tachyon coupling to survive and allow it to describe dynamics. And what's happening is that when the theory flows to the infrared, the metric is so strongly curved that string theory can't tell the difference. It's sort of like the tachyon couplings and metric couplings start mixing strongly. You know, how to say this? If you're doing a normalization group flow and you have two fields that are nearly the same dimension, they can mix strongly under the RG flow. Okay? And so what's happening here is when the metric becomes sufficiently strongly curved, the tachyon and metric perturbations can have roughly the same anomalous dimension, and so they can mix strongly. And so your intuition about what the geometry is completely breaks down. So roughly speaking, this intuition is accurate when the volume of this two-cycle is much, much greater than L string squared, and this applies when the volume of the two-cycle is much, much less than string scale. Right. And so, right. So what's happening, what the rules of the game are, you should just think about BPS conditions on the world sheet, okay? If you want to preserve some space-time supersymmetry, the sort of rule of thumb is you need to preserve some world sheet supersymmetry. So this is, maybe I didn't say that the supersymmetry of this world sheet U1 gauge theory is n equals 2. So this superpotential, the fields are complex. So string theory is already n equals 1 supersymmetry on the world sheet. If the fields are complex, there's an imaginary partner of that supersymmetry. So it's n equals 2 supersymmetry. So z to the n is a BPS operator on the world sheet. And if I'm in the conformal limit, it carries an R charge. Well, it always carries an R charge. So it's BPS on the world sheet with an R charge Q sub R equals 1 over n in somebody's normalization. Okay, and in the conformal limit, the R charges determine the conformal dimensions by the BPS condition. So the dimension of z to the n is 1 over 2n. Sorry. So is a BPS operator, Q sub R of z is 1 over n, sorry. And Q, this is, right, z to the n. Delta of z is 1 over 2n. Okay, so the dimension of z to the n is 1/2. Thank you. Okay, and since I'm integrating d2z, d2 theta, w of z, this is a marginal, a scale invariant operator. So everything's consistent. Right? So basically, the low energy scale invariant limit. I'm going. If I want to do string theory, I want I need my world sheet theory to be conformally invariant so I can impose the Virasoro constraints on the world sheet to get consistent dynamics. And this setup says I indeed have a world sheet superpotential which is conformally invariant. And okay, and so indeed, if this is a dimension, if the integral d2 theta of this is a dimension 1 operator, I've got indeed some tachyon, which is the same conformal dimension as the metric, which is also a 1-1 operator, and so indeed they can be mixing strongly. Okay. All right. So all of that was a long-winded warm-up to coming back to this question of an ALE singularity. So this is some story that Witten applied to describing compact Calabi-Yau manifolds, right? My U1, my deterrent constraint gave me CPN, and then the superpotential carved out some subspace of CPN, so my target geometry is compact. What we'd like to do is, if we're going to be describing some kind of world sheet dynamics in the presence of this decoupling story, we'd like some kind of way of transferring all of those considerations to a non-compact Calabi-Yau, some ambient geometry with just a local Calabi-Yau singularity, and what would that look like? Well, so an AN singularity is what? It's z1 to the n plus z2 squared plus z3 squared equals 0, not in CP3, but in C3. And so, right. Now, right. So we want the same sort of local structure, that gave us some kind of world sheet superpotential describing the structure of our non-compact Calabi-Yau. And here the data suggests that maybe, if this is the superpotential condition I'm describing, z1 to the n should be part of the superpotential on the world sheet that's describing that. The z2 squared plus z3 squared is kind of trivial, right? This is just a couple of massive superfields, so you can ignore them. But we need something that tells us there are directions we can go away from the singularity which are non-compact. And so we need a field space direction which is non-compact, i.e. the direction we can go away from this singularity out to infinity. Okay, and well, I could bullshit for a bit more, but maybe I should just give you the answer. The answer is to couple W equals z to the n to n equals 2 Liouville theory. So what is Liouville theory? It's the theory with an exponential potential. If we're going to do it with n equals 2, we want an exponential superpotential. And so our W is z to the n plus, call it mu naught, e to the minus n beta phi. Okay. So the sort of division of labor here is this is going to represent the structure of the Calabi-Yau singularity, and this is going to give you the non-compact directions going away from it. Now, another thing that for those of you who know a little bit about how Liouville theory works is that in addition to this superpotential, the world sheet dynamics has a linear dilaton. So this is also fitting into what you might expect if this is going to be describing the decoupling limit of this structure, and it's, on the other hand, equivalent to little string theory, then somehow a linear dilettante has to get into the game. And here it is in this theory. Okay. More generally, we can deform the superpotential by marginal perturbations. Okay. So I could write more generally a superpotential which is z to the n plus, say, mu n minus 1, z to the n minus 1, e to the minus beta phi, plus dot dot dot, plus mu naught e to the minus n beta phi, or, in other words, product I equals 1 to n of z minus some other parameter, call it lambda I, e to the minus beta phi. And the interpretation that Givon and Kutasov gave this is that that this is, on the one hand, some description of something that looks a little bit more like you're describing, hypersurface singularities. And so their interpretation was that you should think of this superpotential as describing some kind of resolved Calabi-Yau singularity, which is basically something like W of z plus x squared plus y squared, some trivial additions, equals 0 in C3. Okay. And so these lambda i's are, in some sense, the locations of something in space-time. And the interpretation they gave was that the lambda i's are locations of underlying NS5 structure. Or equivalently, you could think of them also as being the locations of the north and south poles of the vanishing cycles of the ALE singularity. And so the structure is an example of that is this case, okay, which is basically like what is this in terms of a factored polynomial? So this, let's call this star. Star is lambda I equal e to the 2 pi I m over n5, where m equals 0 up to n5 minus 1. So that's why I'm saying they're like the locations of the 5 branes in some transverse plane. That this superpotential should be considered to be what you would get if you put the 5 branes arrayed in a circle, evenly spaced, 1 up to n5 of them. And so there's actually quite a lot of evidence for this, because there are various things you can compute in the worldsheet theory. That I'll tell you about in just a second. Okay. So this would all be pretty useless if you didn't have some way of solving worldsheet string theory in the presence of this superpotential. And if I handed you some scalar field theory, said, okay, go, solve this non-trivial conformal field theory with a superpotential z to the n, and then go solve, this non-trivial theory with an exponential superpotential. Come back to me after you solve that, and I'll tell you how to do string theory in this background. Okay. But fortunately for us, that work has already been done. Facts. So the superconformal field theory, so 1 plus 1D superconformal field theory with W equals Z to the N is the same thing as the SU2 Wess-Zumino-Witten model with a certain U1 subgroup gauged. So gauged Wess-Zumino-Witten model. What do I mean by that? I mean, you do two-dimensional Kern algebra representation theory, which is completely understood, and you select the subgroup, the subset of the representations that are invariant under some U1 subalgebra. So again, completely canonical. So this is a theory which is completely well understood, and it turns out that it's exactly equivalent as a quantum field theory to this thing here. So that's fact number one.
So where does the N go in the gauge? In the gauge WW, where does the little N go?
So I want to come back to my Calabi-Yau. So I want this to be Z to the N5, so that the roots of unity are N5 in character.
The level.
And so this is the level of the Wess-Zumino-Witten model, of the SU2 Kern algebra. Okay. And so that's the story for the compact part. The non-compact part is just change SU2 to SL2. So n equals 2 Liebel. Is equivalent as a quantum field theory to SL2R mod U1. Again, level N5. Gauged Wess-Zumino-Witten model. And so, right. So the claim is that these equivalences of quantum field theories are an explanation of the equivalence of the two decoupling limits. One description as 2A on some Calabi-Yau singularity. That's basically the presentation I've given you here, where the superpotential encodes the structure of the Calabi-Yau singularity. And the claim is that this other presentation is the decoupling limit of the 5 branes. And so this relates to, well, it's not original to us, but it's something that Stefano Masai, David Turton, and I have been exploring for the last couple of years. There's a variant. There's a variant of this theory. So SU2 mod U1 cross SL2 mod U1 can be equally well thought of as SU2 times SL2 mod U1 left cross U1 right, where the U1 left is generated by the J3s in the two Lie algebras, and the U1 right is the corresponding things with J3 bar. Why do I say that? Because you can work out very explicitly what this theory is. you write down SWZW, and then you gauge it. So you write down A, J, let's call this thing J without scripts, and J bar without scripts. So you write down A, J bar plus A bar, J, and then it turns out for gauge invariance, you need an additional term. In order to describe that term, I need to lay down some coordinates on the group manifold. So SL2 can be written in so-called Euler angles, e to the I, tau plus sigma, sigma 3, e to the rho, sigma 2, e to the I, tau minus sigma, sigma 3 over 2. And similarly for SU2, same thing with Euler angle coordinates phi plus psi, theta, and with an I theta, and phi minus psi. Okay. So these are the standard global, so SL2R is the same thing as ADS3 as a manifold. So these are the standard global coordinates on ADS3. So rho is the radial coordinate, tau moves you up the boundary, sigma moves you around. Okay, and then the corresponding things for the SU2. And what are you gauging? You're gauging simultaneous translations in these Euler angle coordinates, the ones on the outside. So if you trace it through, you can find that tau minus phi is gauge invariant. And similarly for sigma minus psi. You can see it from here, right? If you just take right, so J3 left is translating this and this. So the sum of these two is transforming under a gauge transformation. The difference between these two is gauge invariant. And similarly, the difference between these two, and you take linear combinations and you get these. Okay. So now let me write down some gauge invariant objects. Sinh rho cos theta e to the I sigma minus psi, and cosh rho sine theta e to the I tau minus phi. So those are two gauge invariant combinations of things I can write down. And those of you who know a little bit about the geometries that Nick and Joseph love, this is just a description of flat space and some funny coordinates called bipolar coordinates. And this is R4 and bipolar coordinates. And what is, whoops, got it backwards. 3 plus 4, 1 plus 2. Right? So, rho equals 0 and theta equals pi over 2 is the unit circle in x1 plus ix2. But rho equals 0 and theta equals pi over 2 is the origin in 3 and 4. And so, so the statement that in this description I was describing some kind of fibranes arrayed in a circle. That circle is the unit circle here, I claim. And one can see it, from the careful evaluation of the Wessamino-Witten structure, that sorry. So in this description of things, there's a map to what's going on in Cartesian coordinates in the transverse space to some fibranes. And then this is what sits here is sinh squared rho plus cosine squared theta. So if you integrate out the gauge field, so of course this as a group manifold, if I do string theory on a group manifold, the dilaton is constant. Okay. But if I gauge some subgroup, the dilaton picks up a factor of the volume of the gauge orbits. So anybody who's familiar with how T-duality works on the worldsheet, it works by doing what's called a Busher transformation. And the Busher transformation is precisely gauging a U1 and writing it in dual coordinates. And so in the same way that the dilaton picks up a factor under T-duality, it's basically, again, this factor, the coefficient of AA bar. So you get a dilaton that looks like this. If you rewrite it in these coordinates, it's exactly the Z5 that I wrote at the beginning of the lecture. And furthermore, you see that there's some kind of singularity going on when rho equals 0 and theta equals pi over 2. This thing vanishes, so the dilaton is blowing up. And that's where the fibranes are. The fibranes are at the bottom of some kind of linear dilaton throat. And so indeed, that's the unit circle in x1, x2, so it's an indication that my fibranes are spread out along that circle. And this picture tells you that they're actually not just spread out along that circle, but they're evenly spaced in units of 1 over n5. All right. So most of what we know about little string theory then comes from, it comes from being able to analyze the worldsheet theory exactly. Okay, it's all current algebra and group theory. So, for instance, this gap that I couldn't get straight at the beginning is a question about what is the representation theory of SL2 times SU2. Well, what's the spectrum of SL2? It's J minus 1 over, if you get the normalization right, N5. I think I see what's going on. Right. And so, as I said, the continuous series representations are a half plus I lambda. And I seem to be recovering the same mistake. Well, the continuum of a gap is basically traces in this language to the fact that continuous series representations, which are plane waves in the radial direction of the SL2R, have this offset in the spin, which leads to a shift in the national condition. I see we're approaching lunchtime. Right. So let me say a few more things, and then I'll stop. So this construction is nice because it says not only can we deal with supergravity in this decoupled theory, we can deal with the full perturbative string theory. In particular, we started off at the beginning saying that we're in trouble because if we put all the 5 branes together, the linear dilaton throat goes on forever. And we run into a strong coupling region where perturbative string theory breaks down. Now, I just told you that this particular background is one where the 5 branes have been pulled apart onto the unit circle in the 1-2 plane. And that string theory in that background is described by this Kern algebra. And the gauging just amounts to selecting the subset of the correlation functions of this Kern algebra theory that are invariant under some U1s. Now, the Kern algebra correlation functions, they're just governed by group theory. They're not singular at all. And the gauging is just doing some kind of BRST cohomology which selects a subset of those non-singular things that are gauge invariant. So the worldsheet dynamics, the S matrix of the worldsheet theory is completely non-singular because we have an exact construction. You can write down, for instance, the 2 and 3 point functions here are determined, been written down, and so on. So everything's fine. So what happened to the strong coupling singularity? Well, the statement is that that string theory, in the presence of a whole bunch of 5 branes that are on top of each other, that's singular. Strings go all the way down to the strong coupling region and get destroyed. They dissolve into little strings or whatever. We lose track of them. But string theory in the presence of a 5 brane throat, but one where the 5 branes have been pulled apart a little bit, is non-singular. And you can see it here. Okay? Basically, what's going on is this scale mu naught is the radius of this circle. And there's an explicit exponential wall that's keeping you out of the strong. There's a linear dilaton that grows large as phi goes to minus infinity. But the Liouville wall, so there's some potential. Okay. And strings that are trying to get here, where there's strong coupling, just get repelled. They can't get to strong coupling. So there's no strong coupling singularity anymore as soon as you pull the 5 branes apart a little bit. And when I was babbling earlier about your geometrical intuitions can mislead you, this is an example of that, right? Here, it looks like the dilaton is blowing up on this circle. That's because supergravity gives you the source that's smeared over this circle. And the supergravity doesn't distinguish where these individual 5 branes are because, right, this circle is some angular direction on the 3-sphere. The 3-sphere has radius square root of n5. So the spacing between these 5 branes is 1 over square root of n5 in string units. Their spacing is way, way smaller than the string scale, and so supergravity can't resolve it. And so it just says, okay, well, I'll just smear over the source, and a 1 over r squared singularity after smearing becomes a 1 over r singularity. It's still singular. And so supergravity predicts the dilaton blows up here. But string theory is smarter than that. It knows that, that secretly the dilaton is sort of regulated by the amount by which you pulled the 5 branes apart. And pushing the 5 branes back together is sending mu naught to 0. That's sending the Liouville wall off into the strong coupling region where the more and more you try to turn off the Liouville potential, at fixed energy, the dilaton gets progressively. So the turning point of any string scattering experiment for fixed energy, eventually, as the dilaton, as the Liouville wall gets moved further and further back, that turning point gets stronger and stronger coupled, and so eventually string perturbation theory breaks down. But as long as you pull them apart, string perturbation theory is perfectly consistent. Okay. And so Yvon and Kutuzov and their Israeli collaborators have made a living out of exploring the details of this construction more and more, calculating more and more correlation functions, determining, you could use SL2 to also say things about the Euclidean black 5 branes, which is closely related construction, so on and so forth. Let me mention one more thing, which is we started with sort of R51 times this structure, the SL2 times SU2 mod U1 left cross U1 right. But if we're doing string theory, really anything will do as long as we can make up the critical dimension. And so it turns out they've also explored situations where you make this R31. You say, well, now I don't, so before when it was R51, okay, I have 6 dimensions here, I have 6 dimensions here, and I get rid of 2 of them by gauging. So it's 9 + 1 dimensional target space. So what are you doing when you make this R31? Isn't that, doesn't that break the rules of string theory where the target space has to be 10 dimensional? And the answer is no. The slope of the linear dilaton, so the dilaton being Q times rho, where this phi here is rho plus I, rho plus I y. So this linear dilaton can be whatever it needs to be in order to solve the critical dimension condition. So the central charge of the Liouville theory is something like 1 plus 3q squared. So by dialing q, so there's a particular value of q equals 1 over square root of n5, which makes things work for R51. But if you say, I want R31, there's some other value of q just needs to be a little bit bigger. And you get critical string theory. So what is that? Well, it turns out that basically what you're saying is that I could add a Z4 squared here and have a Calabi-Yau threefold singularity. The Z4 flowing to its infrared is just some massive theory. And so what's happening is that as you flow to the infrared with this superpotential, these things go away, but their sort of residue is felt in the space-time dimension, which is made up by the Liouville theory. So in terms of thinking about Calabi-Yau n-fold singularities, you could do the same thing you did for an ALE singularity if you were interested in some other kind of hypersurface singularity in a Calabi-Yau n-fold. And so, and then you can play this game of replacing this by any kind of, P of Z1 and Z2, say plus Z3 squared plus Z4 squared equals 0. Well, actually, you're resolving the singularity a little bit, so it's sort of like mu naught e to the minus beta phi, as I was writing before. And so when you send mu naught to infinity, that's when you get the singularity where all the phi branes come together. The corresponding Calabi-Yau hypersurface singularity is this polynomial equals 0. But now, instead of just being like z1 to the n equals 0, it's some kind of polynomial hypersurface in 2 variables, which is a Riemann surface. And so the interpretation that Givon and Kutuzov give is that this sort of theory and its generalization to more general Landau-Ginzburg singularities is that you're describing an NS5 wrapped on a Riemann surface P of Z1, Z2 equals mu naught. So it's a kind of resolved singularity. And this is interesting because the phi branes now are giving you something in 3 plus, the non-convex directions are 3 plus 1. So instead of being 5 plus 1 Yang-Mills theory, it's some kind of weird strong coupling limit of 3 plus 1 gauge theory. And they presented a fair amount of evidence that in this class of theories are various sorts of Argyros-Douglas singularities. Right. So if you had the 2-0 theory in 5+1 dimensions as some kind of infrared strong coupling limit when you pushed all the phi branes together, then it makes sense that if you're in 3+1 dimensions, you can get other interesting super conformal field theories as governing the infrared dynamics. And so the claim is that you've got some kind of resolved conifold singularity if you wrap a phi brane around it in, I guess, type 2a, that the infrared dynamics should be, other interesting things. And unfortunately, this whole game, the reason you were able to solve string theory is that you're in a situation where you're very far from studying that non-trivial infrared dynamics. You pulled the phi branes apart in order to get rid of the strong coupling singularity and make worldsheet string theory weakly coupled. And right, but at the same time, right, if your sort of W objects are branes that are stretching between the phi branes, or wrapping the cycles of the Calabi-Yau singularity, as soon as you resolve the Calabi-Yau singularity and make it sort of finite size, you've made all of the interesting non-abelian structure massive. So the very thing that makes perturbative string theory solvable is the thing that makes the interesting non-abelian gauge dynamics trivial, by massing it all up. And so on the one hand, it's very tantalizing that we have situations where we can solve string theory exactly in some decoupled theory that's not just a field theory, but a full string theory. But some of the hardest parts of that, which is what happens when you push the singularity to its singular limit to get to the most interesting aspects of the dynamics become strongly coupled before you can access it. And so perturbative string theory methods break down. But anyway, that's sort of like an overview of what's been going on for the last 20 years. You can do things like, well, what you do in, when you're learning string theory, well, when some people are learning string theory, they learn how to compute the string S matrix in flat space and get, the Veneziano formula. All of that exists here in some much more non-trivial background. And for instance, as I said earlier, there's a Penrose diagram, right? So it's not just that you have gauge theory correlation functions and you're supposed to compute the gauge theory correlation functions to infer things about supergravity. The string theory has scattering states and an S matrix, and so maybe this is the last thing I should say. You've got this throat. You've sort of capped it off at some scale that's set by this mu naught. And you can send strings in and get them back out. There's an actual string S matrix. So it's not just you calculate Green's functions. You calculate S matrices here. But those S matrices have poles. Where are the poles? Well, like in any scattering problem, the poles in the S matrix are the locations of the bound states in the energy plane. And so where are the bound states? There are things that are sitting down here in the bottom of a cap, rattling around, but having some exponentially decaying wave function. So in fact, the structure here, the representation theory of SL2 is there are continuous series representations and discrete series representations. And the continuous series describe the scattering states, things that are plane waves in the radial direction. The bound states, the discrete series representations have wave functions that go like e to the minus alpha rho. They're bound. Okay, they're exponentially decaying up the throat. And so if you wanted to calculate Green's functions for the gauge dynamics on the phi brane, the prescription is you calculate the string S matrix, you extract the residue of the poles, like you would in some standard LSZ prescription. The residue of the poles recovers the bound states and their interactions with each other. If you calculate higher and higher point functions in the string scattering and extract the poles in each of the asymptotic states, then the residue of the pole claim is the Green's function, the off-shell Green's function of the gauge theory dynamics on the phi branes, right? Because it's the states that live down here at the bottom of the cap that are bound to the phi branes that are related to the intrinsically phi brane dynamics. So there's a whole rich literature of how you calculate things in string theory. You use them to infer things about the strong coupling gauge dynamics. It's just not quite in the regime where you would like to study it, where it's fully non-abelian. Well, hope springs eternal. Let me stop there.
Questions?
Oh.
So the silly and stupid question. I mean, this prescription that you get in 60, the volume theory is superamines with n equal 1,1 supersymmetry, right?
Yes.
And the little string states can be realized as BPS states of this superamines.
Mm-hmm.
But if you reduce this superamines slightly on the circle, you get n equals 4 maximum superamines in 5D.
Yes.
But the non-story is that we know that the n equals 4 5D MES is not renormalizable power counting, so you are for its strong coupling limit. But it is the 2,0 60 SFT with the little string state, and not the one that you described. Is there a quick answer to this?
Well, it's true that if you reduce the, so let's see, if I get this straight. The 2-0 theory reduced to 5 dimensions is definitely Yang-Mills theory, where the gauge boson is you just put one of the legs of the self-dual tensor on the circle you're compactifying on.
Exactly.
Yeah, so that's in 2A. But the claim is, right. This straight. So I think it's just an order of limits thing. So we're starting with little string theory in 5 plus 1D. And what we've kept fixed is there's some scale L strength. Now, it has two flavors depending on whether you're in 2A or 2B. Okay, if you're in 2A, then the IR is the 2-0 theory, so the self-dual tensor multiplet in 5 plus 1. Right, and that's at scales much less than L string. Then if you're in 2B, little string theory in 5 plus 1B, again, goes to 5 plus 1, the super Yang-Mills, with coupling L string squared. So in this description, I can't really get away from having L string. L string is kind of the scale I've kept around, right? This theory at scales much less than LS goes to a superconformal fixed point. So you can take that superconformal fixed point theory and further compactify it on some circle, and then so this is right. So this goes to superconformal field theory with 2-0 supersymmetry. That theory has no scales, You can take that theory that has no scale and introduce a scale by compactifying it to 5 dimensions. The only scale in the problem now is the radius of the circle.
Yes.
Okay. In playing this game where you've kept the scale L string around, okay, then I'm really talking about something else. Because when you compactify this theory, there are now 2 scales. There's the scale L string, and there's the scale, the radius of the compactification. Okay. And so once I have both of those scales, I have R and LS, and I know that this theory has T-duality, then I'm saying that the theory on the circle of radius R in 2B is the same thing as the theory on the circle of radius L string squared over R in 2A, which is the standard T-duality relation. Okay? But in order to do that, I need both of these scales to be finite relative to L string. And not this story, which is to take the infrared limit first, to decouple this scale, and then compactify it in finite volume. So it's a slightly different limit.